Welcome back. Now, what we are looking at the reasons for the pair potential limitation, and then we go into the atomic stress. So, number one is, if you look at this slide, there are some good points made here by Marcus Buehler, who teaches similar course at MIT, that in pair potential, the strength of each bond is independent only on the distance between the two atoms involved. So, what we are looking at, the strength of each bond is independent based and depends on the distance between the bond. So, if you look at in quantum mechanical way, it tells us that the strength of bond between the two atoms is affected by the environment. So, what is the pair potential doing? Not taking care of the environment. That is where the anomaly comes from. As a site becomes more crowded by the other bond, strength will generally decrease as a result of Pauli's repulsion between the electrons. The modeling of many important physical and chemical property depends crucially on the ability of potential to adapt to the environment. And if you look at, that is where it cannot reproduce the surface relaxation properly, because it is only looking at the pair of the potential. That is where the many body potentials are required. Now, let us turn our attention to the main idea about the atomic stress. Atomic stress is very important concept, because as compared to continuum, where it is almost like a surface, in the atomic stress everything is a particle. So, there is a particle, and the particles are connected in terms of atoms with a spring, and number of those springs are creating the stress and strain behavior. So, if you look at, they are connected in different directions. So, there is a directionality, and you already know that spring constant that we put into in a hydrocarbon chain or molecules which are polymeric, that is where lots of spring action is happening in a very different way. So, how do we define atomic stress? So, we want to relate continuum stress with the atomic stress, and what we are looking at, the typically continuum variable represent the time, space, average microscopic quantities of the equilibrium. So, we are looking at the equilibrium, this is the macroscopic model, but what we are looking at, the continuum variables are essentially looking at the average time and space average of the microscopic quantities. So, this is where what we are looking at, the difference between the atomic stress and the continuum stress is the continuum properties are valid at a specific material point. This is not true for atomic quantities, these are the discrete nature of the atomic microstructures. So, now if you look at continuum, which is just a flat surface, for example here, and if you look at on your slide discrete fields, and if you are putting stress in some of the locations which are interstitial between atoms, you will have very different behavior than if you were hitting or trying to stress the particle itself. In continuum, all of these things become one plane. So, no matter where you put your stress, it is same. But as you go to atomic level, then there are sites where atoms are available, and there are sites where atoms are not available, which are called interstitial sites. So, if you apply atomic force microscopy or some such experiment, you will see that there are different kinds of peaks and valleys because of the locations of the atomic structure, and that is where atomic stress becomes very different. So, if you look at the virial theorem, which we had talked about, of the pressure, calculation of the pressure, then we can define the sigma 1 as 1 over omega, which is the volume, and then you are looking at the atoms alpha and atom beta. So, if you look at two atom alpha and beta, and if you look at the force working on it, and there are other atoms around it, and the distance between these two is r alpha beta, then mass of atom alpha multiplied by u alpha, these are the velocities of alpha particle at time t, and you are also looking at alpha j. So, you are looking at I and j. So, these are the pair of atoms, their masses, and we are summing up all the pressures, the interaction here, plus you have the what we call is the force term. Force term is coming from your potential energy function d phi r over dr. Now, you are multiplying that by r I over r, and then the r j, which is a particle j interacting with particle I, and that is where r alpha, which is when r becomes the bond length between r I and r j. So, this is kind of at the atomic level we are defining stress with terms of its what we can call as momentum of the atom and of the pair of atoms, and also the force between the pair of atoms, and that gives the atomic stress. And you can then define it for virial stress for one dimensional. So, in this case we are just looking at one dimension of, let us say, particle 2, and it has particle 1 and 3 in one dimensions. So, the 2 is having force from 1 as well as 3. So, now here you look at R 2 1 and R 2 3. So, if you now just take this one dimensional stress, so sigma 1 2 is 1 over omega, which is the volume where these 3 particles are sitting in a box. 1/2 we are looking at two sides, and summation of alpha beta, where alpha is not equal to beta, we are looking at 1 2 and 2 3. That is where d phi r over d r. So, if you look at this formulation of stress, then force between two particles obviously is this term, which is the potential energy function d phi over d r, and then sigma 1 1 in that case become 1 over sigma. Again, this is a very simplified one dimensional half of f 1 r 2 1, this is the distance r 2 1, and f 2 r 2 3, this is the bond length between the two. So, it comes down to a very simple expression. So, this is what we are looking at. So, the question now is that how do we calculate the elastic constant. So, let me go back to document camera and show you some derivation there for the calculation of elastic constants. So, now we come down to the stress and strain in a particular situation. So, we already know the virial theorem, which is giving us good idea about the momentum and the velocity. So, now we are going to look at a Lagrangian for the strain tensor. So, we start with a very simple idea about for the elastic constant. So, let us say we define a Lagrangian strain tensor, and let me remind you Lagrangian L is equal to k minus u, which is kinetic energy and potential energy. So, this is where we are going to reformulate. So, if you look at that n I j, we are looking at I j again is the strain directions, 1 1 is the principal, etc., that you already know. That becomes half of the we are defining a term j, which is deformation tensor, which is almost like elastic constants, but it is the trace multiplied by j minus 1. This is the tensor we are looking at. So, if you look at j is the deformation tensor here. So, that relates stress and strain. So, if you go from position x to y, then using the deformation tensor. So, let us say if you were in any point x, and now this particle due to deformation goes to y. So, this is where we look at y then becomes j, which is the deformation tensor, and x vector. These are both vectors. So, this is similar to what you saw earlier, where sigma I j is equal to k I j k l multiplied by strain k l. So, this is similar corresponding to this model, but we are just simplifying it for our purpose of definition of the elastic constant. So, with this, if we have to calculate elastic constant, then we use the Helmholtz free energy. So, we are using energy and using the laws of thermodynamics to understand the changes in the elastic constant. So, in this case we are looking at I j k l, that we already know the tensor, that is equal to 1 over v in terms of Helmholtz free energy, d n I j, which is the strain, and we are looking at n k l. So, we are looking at both quantities here. So, this is what gives us, using the energy formulation, for elastic constant, and we'll learn about that in a minute, but let me just put that as the portion that we are going to look at. So, now if you have this information available to you, then we are able to calculate C, let us say C 11, which is what we want, T, that is equal to 1 over V K B multiplied by temperature, and we are now using thermodynamic the functions which are averaged. So, this is average sign. So, summation of phi, which is the potential energy R delta R square, minus, now you are looking at summation of phi dash R over delta R complete square. So, this is almost like standard deviation formulas that you do. This is the individual and this is the essentially the average minus the particular condition, plus now we have to do 1 over V. Now, we look at the second order terms. So, this is like an expansion phi double R over R square delta R, which is the deformation term only in x direction, minus 1 over V. We now look at summation phi dash R cube delta x R 4, plus we have to add the 2 n k b t over V, that is essentially the term looking at the whole thermodynamic energy term here. So, this is C 11. So, similarly you can do C 12 and C and also C 44. So, this gives you a molecular dynamics model to calculate different elastic constant, and we will also look at the Parinello-Raymond condition with the flexible cell. You can also calculate that, but in this case you are looking at energy formation. So, if you look at a cubic crystal, and we are going to look at cubic crystal, and if it is isotropic cubic crystal, what that does to us is very important to know. So, in that case C 11 C is equal to C 22 is equal to C 33. So, all we need to know is C 11, and out of C 12 is equal to C 21 is equal to C 13 is equal to C 31 is equal to C 23 equal to C 32. So, that means all we need to know from here is C 12, and the third one is C 44 is equal to C 55 is equal to C 66. So, all we need to know is C 44. So, for a cubic crystal, that I will show you a case study where I calculated the elastic constant for cubic face centered cubic copper. All you need to know is C 11, C 12 and C 44. That is the calculation we are going to do for different substances, and we will develop a table, and then we will make sure that these different constants work. So, this is how we are essentially going to now look at the different elastic constants in the context of the stress. So, let me stop here, and then we will go to the next section. Thank you.